Use the chain rule with the power rule. Alright, so in this video we're going to introduce what the chain rule is, and we're going to discuss when we need to use the chain rule. So what is the chain rule? Well, the chain rule is our differentiation method for finding the derivative of composite functions. And if we remember back to pre-calculus, hopefully you remember that composite functions are functions inside of another function. So basically the chain rule is taking the derivative of a function which is inside of another function. Now there are a bunch of different notations, a bunch of different methods, but they all represent taking the derivative of the function inside a function. We're going to go over a couple of those different notations. Please feel free to use whichever notation is best for you. One is not better than the other. Alright, so our first version, we are going to let y equal a composite function. More specifically, we're going to let y equals f of g of x. So here we can see that the outer function is f, and the inner function is g. So then when we want to come in and we want to take the derivative of this, here's how the derivative works. First, we want to take the derivative of the outside function, because we work our way from outside in. So dy dx is first going to equal f prime of g of x. So again, we're taking the derivative of the outside, but we're going to leave the inside alone. So in our first step, we don't touch the inside. We just leave it alone, but we take the derivative of the outer function. Then, since we have taken the derivative of the outer, but we haven't taken the derivative of the inner function yet, we're then going to multiply that by the derivative of the inside. Or if we wanted to put this into words, we could say dy dx is equal to the derivative of the outside, we leave the inside alone, and then we multiply by the derivative of the inside. And that's the chain rule version 1. Alright, let's take a look at our next version, version 2. So in version 2, we're just going to change the notation a little bit. We're still going to let y equals f of g of x, but this time, instead of having g of x as our notation, we're going to substitute in u for g of x. So it looks like we just have a function of f of u. And ha ha ha, best math thing ever, it's the fu function. Ha! Alright, so with this notation we're going to find the derivative of the fu function. So in order to do that, we're going to come in, we're going to take the derivative, and the same process applies. We're going to take the derivative of the outside first. So y prime is going to equal f prime of u, and u remains inside, protected, untouched. Then we're going to multiply by the derivative of the inside, which is u. So to take the derivative of the fu function, giggle, 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 y prime is equal to f prime of u times u prime. And students often prefer this particular notation because it's a lot easier to visualize having a u as opposed to a g of x. But again, use whichever method works for you. Alright, now on to our third version. So this is version 3, so again, we're just going to change things around a little bit more. And we're going to, go a little bit drastic this time, because what we're going to do is we're going to let y equals Tony Stark inside of Iron Man. Because that's obviously a composite function. We have Tony Stark inside of Iron Man, f of g of x. So if we want to take the derivative of Tony Stark inside of Iron Man, we'd have dy over dx. And again, we would start with the outer function, which is Iron Man. But we know that we are going to want to take the derivative of the outer function first. So, in order to take the derivative of Iron Man, we're going to ask our good old pal the Hulk to come by. And in order to take the derivative, we're going to Hulk smash Iron Man. So let's go ahead, let's take the derivative. So Hulk smash! And we're left with a broken Iron Man, hence derivative of the outside. But Tony Stark stays nice and protected on the inside, our untouched inner function. So now that Iron Man has kind of been, derivatized, Tony Stark then jumps out and he escapes. So now we have the inner function running around, but we know we want to take the derivative of the inner function as well. So Hulk comes over and he's like, Hulk smash! And we take the derivative of Tony Stark. So Hulk smash! Pff. And then we are left with the derivative version of Tony Stark, which are his sunglasses, or Edith. And there we go. The chain rule. Because the smashed up Iron Man with Tony Stark on the inside is our f prime of g. The outside is the derivative. The inside is untouched. And then the g prime is Edith, the sunglasses that are left over. And there you go. There is my favorite version of the chain rule. All right, so let's take a look at an example now. So here we're going to let h of x equal f of g of x. So we have a composite function. So before we read any of the other information on this page, let's just start out with that. We know that h of x is equal to f of g of x. And we're going to want to take the derivative, and we know that when we take the derivative of a composite function, we're going to take the derivative of the outer function first. We're going to Hulk smash it, and we're going to leave the inside nice and alone. Tony Stark inside, nice and safe. Well, then Tony Stark escapes, and Hulk smash to find the derivative. So there's our formula. Now that we have our formula for the chain rule, we can go ahead and read the other information, and then we can use that to actually answer the question. So we're told that f of negative 4 is negative 6. We are told f prime of negative 4 is 4. G of 3 is negative 4, and g prime of 3 is 5. And we're being asked to find h prime of 3. So that means x equals 3, so we'll go ahead and we can plug that in to our derivative. So h prime of 3 is going to be equal to f prime of g of 3, and then times the derivative of g prime of 3. All right, well, let's see. We can't evaluate f prime until we evaluate the inside. So the first thing we're going to have to do is we're going to have to substitute in the value for g of 3. Unfortunately, we know the value for g of 3 is negative 4. So we can go ahead and we can substitute that in. So we're going to get f prime of, and we said g of 3 is negative 4. Well, we also know g prime of 3. We're told in the problem that g prime of 3 is 5. So then we can go ahead and substitute that in. And now next up, let's see, we have f prime of negative 4. And wouldn't you know it, we're given that piece of information in the problem as well. So now we can substitute in f prime of negative 4 for just being 4. We can bring down the 5, and then we can do the nice, simple, easy step of 4 times 5, which will give us 20. And there we go. H prime of 3 is equal to 20. And then just one final thing to point out here. We can see that there is one piece of information that we didn't use, and that is A-OK. This is Newton's form of trying to trick you into thinking you did something wrong. Because it's like, well, I didn't use that piece of information, so I must have done something wrong. But no, don't fall for it. That's a trap. We're better than Newton, so you can leave that piece of information alone. All right, let's take a look at a similar example. So again, we're going to let h of x equals f of g of x. And we're told f of negative 3 equals negative 1, f prime of negative 3 equals negative 5, g of 5 equals negative 3, and g prime of 5 equals negative 4. And we're being asked to find h prime of 5. So we can start off the same way we did before. We know that h of x is going to be equal to f prime. Oh, sorry, no derivative yet. Dang it, dang it, dang it. H of x is going to be equal to f of g of x. Sorry, I'm too eager to take the derivative. Chain rule, chain rule, chain rule. Now we can take the derivative. So now we'll Hulk smash f to take the derivative. So f prime of g of x, and then we'll multiply by the derivative of the inside, which is g prime of x. But we don't want to have the general derivative. We want to find the derivative of a specific x value, which is 5. So then we can come and we can substitute that 5 in. So we're going to f prime of g of 5 times g prime of 5. And just like before, we can start plugging in what we know. We know that g of 5 is going to be negative 3. So that's going to give us f prime of negative 3. And we know that g prime of 5 is going to be negative 4. Now that we have f prime of negative 3, we do see that we have that piece of information in our problem too. So we can substitute that in, giving us negative 5 times negative 4. And we are left with a derivative of h at x equals 5 of 20. And as you can see before, they tried to trick us. They gave us a piece of information that is not needed. All right, so next up, we're going to be asked to do the same thing, find the derivative of h of x, but this time we're being asked to use a table to evaluate this. So this is a little bit different, but it's a bit the same. So let's just take a look at this. So we're going to suppose h of x is equal to f of g of x, a composite function as usual. And we're going to use the table now to find the derivative at x equals 2. All right, so if we are going to take the derivative of h of x, we know that's going to be h prime of x is equal to f prime of g of x times g prime of x. But again, we're not trying to find h prime, we're trying to find h prime of 2. Excuse me, we're not trying to find h prime of x, we're trying to find h prime of 2. So we can substitute that in, f prime of g of 2 times g prime of 2. So looking at this table, we need to evaluate, or we're trying to substitute values in, for g of 2 and g prime of 2. And we'll notice that with both of these functions, our input is x equals 2. So in our chart, we're going to look at the line of x equals 2. And we can see that when x equals 2, g of x is going to be 3. So we can make that substitution. So we're going to have f prime of 3. And we can see that when x equals 2, g prime of x is going to be 5. So we can make that substitution. And then, next up, we're trying to evaluate f prime of 3. So in this case, x is now equal to 3, so we'll look at that row of our table. And we can see that when x equals 3, f prime of x is going to be 5. So then we can make that substitution. So we're going to have 5 times 5, which is going to give us a final derivative of 25. That last step is the best. So next up, we're going to be talking about identifying when the chain rule is needed. And this is probably the most difficult part of the chain rule, is trying to figure out when we have a composite function and what the inside versus the outside of that composite function will be. So, what do we need? Or excuse me, when do we need the chain rule? Well, we need the chain rule when we have a function inside of another function, i.e. composite function. Tony Stark inside of Iron Man. Composite. So let's just take a look at some examples, and we're going to be asked here to decompose the composite function, or write the following functions as two separate functions. So letter A, we have the quantity x cubed plus 3 to the 5th power. And it's always easier to identify the inner function first. So we can see here that x cubed plus 3 is our inner function. So for this particular example, I'm going to use our FU notation. So our inner function here is going to be x cubed plus 3. Then we need to find our outer function, and our outer function is the inner function raised to the 5th power. So that means f of u is going to be, well, we can see that we're going to take our inner function, which is u, and we're going to raise it to the fifth power. And there we have our two functions. We have the inner function of x cubed plus 3 and the outer function of a variable raised to the fifth power. Moving on to letter B, let's do the same thing. We can see that our inside, or in this case our u, is going to be negative x to the fourth minus 3. We can see that our outer function is that inside raised to the negative second power. So therefore our fu is going to be u to the negative second power. And then moving on to letter C, we can see our inside function here is going to be 1 minus 2x to the fifth. And we can see that the outer function is the square root. So therefore f of u is just going to be the square root of u. So inner, outer, inner, outer, inner, outer. Great. Nothing too difficult there. Let's take a look at some more examples, such as trig functions. So here we want to write the following functions as two functions. In the last slide, I used the u and fu notation. This slide, just to change it up, I'll use the g of x and f of x notation. But we're still going to do the same thing. We want to identify the inside function first. So that means we have g of x is equal to tangent of x. And we can see that the outer function is going to be our cosine. So therefore f of g of x is going to be equal to cosine of g of x. So again, we have our outer versus our inner. Then for letter E, sine of 6x squared. Again, we can see that the inner function, or g of x, is 6x squared. And then we can see that our outer function is sine. So f of g of x is going to be sine of g of x. Now, tangent to the fifth power of x is a little bit tricky, because folks sometimes fall into the trap of being like, oh, x is the inner, and tangent's the outer, and then what do I do with this fifth power? And that's the rub here. How does the fifth power change this expression? Well, let's think back to trig, and we know that tangent to the fifth power of x can be rewritten as tangent of x to the fifth power. And when we change the notation to look like this, it's pretty easy to see that the inside function is actually tangent, and the outside function is going to be to the fifth power. So that means our g of x is going to be tangent of x, and our f of g of x is going to be g of x raised to the fifth power. And there you go. We have just decomposed composite expressions. So now that we can do that, how can we apply the chain rule when we want to use the power rule as well, or using the chain rule with the power rule? So we're going to dive in. We're going to take a look at an example that says find the derivative of y equals the quantity 4x minus 1 cubed. So first thing we want to do is we want to identify all of our different pieces. We can see that our inside here is 4x minus 1. And I'm going to use the fu notation, probably because I like saying fu. So that means our u is going to be 4x minus 1. And then our f of u, we can see that our outer function here is going to be that inner function raised to the third power. All right, so that means that we can rewrite our y value as being y equals f of u. So if we want to come take the derivative, so if we want to do f prime, that's going to be derivative of the outside, so f prime, we're going to leave the u alone, and then we're going to multiply by the derivative of u. So we still need a couple more pieces in order to evaluate this derivative. So we do need to take the derivative of u and the derivative of 4x minus 1 is just 4. And if we take the derivative of fu, that's going to be 3 times u to the second power, because we are using the power rule to take the derivative of that expression. All right, so then we can just substitute everything in. So y prime is going to equal f prime of u, and we just found out that f prime of u is 3 times u squared. So we can substitute that in. And we also found out that u prime is going to be 4. Now there's one more substitution we have to make. We have to get rid of the u. And we know that we said u is going to be 4x minus 1. So we'll substitute the 4x minus 1 back in. We'll still multiply by 4. And then the final piece we need to take care of here is we do need to simplify. And all we can really do to simplify here is multiply the 3 by the 4 to get 12 times the quantity 4x minus 1 squared. And there we go, our first derivative with the chain rule. All right, let's take a look at another example. So our second example here is we want to find the derivative of y equals 3 times the quantity x squared plus 9x raised to the negative second power. All right, so we said the first thing we want to do is we always want to identify our inside and our outside function. And we can see here that our inside function, which we'll denote as u, is x squared plus 9x. And then we can see the outside function is going to be 3 times the inside function raised to the negative second power. So that means our f of u is going to be 3 times our u raised to the negative second power. And based on our previous example, we know that we will eventually have to take the derivative of each of these functions. So we will need u prime, and we will need f prime of u. All right, u prime, that's nice and simple. The derivative of x squared is 2x, plus the derivative of 9x is 9. Now to take the derivative of fu, we're going to have to use the power rule here. Power rule says we take the exponent, multiply it by the coefficient, and subtract 1. So let's see, negative 2 times 3 is going to be negative 6 times u, and then negative 2 minus 1 is negative 3. So f prime of u is going to be negative 6 times u to the negative third power. So now we can actually take the derivative, so we know that y is going to be f of u. So when we want to take the derivative, let's use the dy over dx notation here. We know that's going to be the derivative of the outside. We are leaving the inside alone, and then multiplying by the derivative of the inside. And now we'll just substitute these values in. We know that f prime of u is going to be negative 6 times u to the negative third power. And we know that u prime is going to be 2x plus 9. And then we can just substitute in our u value, and that's going to leave us with negative 6 times the quantity, x squared plus 9x raised to the negative third power times 2x plus 9. All right, now there's not much more we can do here. All that's really left is to distribute the 6. Now, some folks like to distribute the 6 into the first quantity, and here we can't distribute this negative 6 into the first quantity because this first quantity has an exponent, and we can't distribute a coefficient into a quantity that has an exponent. So that means we're going to take the negative 6 and we're going to distribute it into the second quantity, which doesn't have an exponent. So that's going to leave us with a final answer of the quantity negative 12x minus 54 times the quantity of x squared plus 9x to the negative third power. And there we have our derivative. Now, if you wanted to show off, you could take this one more step, but you don't have to. Newton does not require it. But you could show your mathematical knowledge by taking the x squared plus 9x and moving it to the denominator to make that 3 positive. Again, that step's not necessary, but I'm going to show off a little bit. Next up, we want to find the derivative of y equals the square root of x to the 4th plus 1. So let's identify the inner and the outer function. We know the inner function is x to the 4th plus 1, And we know the outer function is the square root. So I'm going to set my u equal to x to the fourth plus 1. I'm then going to go ahead and take the derivative of this right away to get 4x cubed. I know that then fu is going to be the square root of x, but I know that I can't take the derivative of a square root. And whoa, that's not the square root of x, excuse me. That is the square root of u. Alright, that mistake is fixed, but going back, we can't take the square root of u, so we need to rewrite this as being u to the 1/2 power, because then we can use the power rule, which means f prime of u is going to be 1/2 u raised to the negative 1/2 power. And now it's chain rule time. So y prime is going to be equal to f prime of u times u prime. And then we can substitute in. So we know f prime of u is 1/2 times u raised to the negative 1/2 power. And we know that u prime is 4x cubed. And then we can just substitute in our u function, which is x to the fourth plus 1, and that is raised to the negative 1/2 power, and then multiplied by 4x cubed. Now we do need to distribute that 1/2, but again, we can't distribute it into this first expression because that first expression has an exponent. But the second expression does not, so we will multiply the 1/2 by 4x cubed, and that's going to leave us with 2x cubed times the quantity x to the fourth plus 1 to the negative 1/2 power. And again, that is our derivative, but if we wanted to show off a little bit, we could, and well, we will. So we're going to get 2x cubed all over the quantity x to the fourth plus 1 raised to the 1/2, which can then be simplified again to be 2x cubed over the quantity x to the fourth plus 1, and that's not what I wanted to write. What I wanted to write was the square root of x to the fourth plus 1. And there we go, there is our showy-offy answer. Alright, now to our last example. Here we want to find the derivative of y equals 1 over the quantity negative x squared plus 3x plus 3 to the fourth power. And oh no! What's the problem here? Well, the problem is that if we wanted to take the derivative of the function as is, we'd have to use the quotient rule. I don't know about you folks, but I want to avoid the quotient rule as much as possible. So, I can use this little trick. I can rewrite this to be negative x squared plus 3x plus 3 raised to the negative fourth power. So that means I can bring the expression in the denominator up to the numerator if I make the exponent negative. And now I can use the power rule with the chain rule. So let's get to it. We can see the inner function here. Our u is going to be negative x squared plus 3x plus 3, which means our u prime is going to be negative 2x plus 3. And then we can see that our outer function is u raised to the negative fourth power. So f of u is going to be the quantity, or u raised to the negative fourth power. And then we want to take the derivative, so f prime of u is going to be negative 4 times u to the negative fifth power, because remember, we want to subtract 1 from the exponent. Alright, so derivative time, dy over dx is going to be equal to f prime of u times u prime. Substitute. We know that f prime of u is going to be negative 4 times u to the negative fifth power. And we know that u prime is going to be negative 2x plus 3. Then we can substitute in the u. So we're going to get negative 4 times the quantity of negative x squared plus 3x plus 3 raised to the negative fifth power times negative 2x plus 3. And then we just need to distribute the 4. And we'll distribute that into the factor that doesn't have the variable. And that is going to give us the final derivative of 8x minus 12 times the quantity negative x squared plus 3x plus 3 raised to the negative fifth power. And as always, well, I guess not as always because you can't always show off, but if we wanted to show off, we could do 8x minus 12 all over the quantity negative x squared plus 3x plus 3 raised to the positive fifth power. But again, both of those answers are acceptable, and both of them are accepted by Newton. All right, folks, that is it. That is using the chain rule with the power rule.